Consider the following vector field. And we have the vector field f defined by components x times the natural exponential raised to the z, y times z squared, and x plus y. And we're asked here to compute the curl of the vector field and to then compute the divergence of the vector field. So we'll keep in mind here that we have a vector in 3 dimensions. So our components are defined as f, g, and h. And then in part A, we are looking for the curl of this vector field. So let's recall that the curl of a vector field in R3 is defined as the cross product of the gradient with your vector field. So if we put this into our 3 by 3 matrix, we have I hat, j hat, k hat of d dx, d dy, d dz. So these are the components of the gradient. And then our vector field is f, g, h. And so we use this matrice to come up or to remind ourselves of the formula for the curl in 3 dimensions. So we have the partial derivative of h with respect to y minus the partial derivative of g with respect to z, I hat, minus the partial derivative of h with respect to x minus the partial derivative of f with respect to z, j hat, plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y, k hat. And what's great about this formula here is that if we are looking at our k component, our z component here, we see that's our 2-dimensional curl. It's a friendly reminder. So now that we've reminded ourselves of this formula, let's go ahead and we'll find the partial derivatives. So we have the f component is defined as x times the natural exponential raised to the z. So we need the partial derivative of f with respect to y, which is 0. And then we also need the partial derivative of f with respect to z, which is just x times the natural exponential raised to the z. We want to do the same thing here with the g component, which is y times z squared. So the partial derivative of g with respect to x is 0. The partial derivative of g with respect to z is going to be 2yz. And then last but not least, we want to find the partial derivatives for the h component, which is x plus y. So the partial derivative of h with respect to x is 1. The partial derivative of h with respect to y is also 1. So we can go ahead now and we'll plug these partial derivatives into the curl formula. So we have the curl of our vector field. Again, we're using this formula above. Can be defined as the partial derivative of h with respect to y, so 1 minus the partial derivative of g with respect to z. So we have 1 minus 2yz, I hat, minus the partial derivative of h with respect to x minus the partial derivative of f with respect to z. So we have 1 minus x times the natural exponential raised to the z, j hat, plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y, which is just 0 minus 0, k hat. And so we can either leave our curl, our vector in this form, 1 minus 2 y z I hat minus 1 minus x times the natural exponential raised to the z j hat plus 0 k hat. That's a beautiful way to leave our answer in our standard unit form. Or if you wanted to convert it to its component form, we would have the x component is 1 minus 2yz. The y component would be minus 1 minus x times the natural exponential raised to the z. And you could distribute that negative sign there as well. I'll leave that up to you. And then the z component is just 0. So either one of these answers is beautiful. They're both equivalent. So then for part B here, we want to compute the divergence of our given vector field. And again, let's start by recalling the divergence formula in 3 dimensions is defined as the gradient dotted with the vector field. So this is going to be a scalar valued result. We have the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. So again, we're going to start by finding the partial derivatives. So again, thinking back, we have the the f component of our vector field is defined as x times the natural exponential raised to the z. We have the g component here is defined as y times z squared. And then our h component is x plus y. So we have the partial derivative of f with respect to x just leaves us with the natural exponential raised to the z. The partial derivative of g with respect to y is equal to z squared. And then last but not least, the partial derivative of h with respect to z is 0. So we can say that therefore the divergence of this vector field, again the gradient dotted with the vector field, is equal to the natural exponential raised to the z plus z squared plus 0. And we really don't even need to include this 0 here. We'll just box up our first 2 components. And so this is our beautiful final answer here for the divergence of this vector field. And then for part A up above, either one of these answers is the final answer for the curl of the vector field.